Okay, so today we're going to discuss bone tissue. And obviously, we have different types of tissues, namely the connective tissue, the tissue that connects all other tissues together. And the most major type of connective tissue we are concerned with is the blood. The blood is a connective tissue. One of the questions on the lab practicals I had for students was, what are the cells in this? What type of tissue is blood? And students um, didn't know, but it was a connective tissue. And then what are the types of cells that are found in the blood? And those are the red blood cells, the white blood cells. Are platelets considered types of a cell? No, platelets are fragments of cells. They are not cells. But the white bloods are cells, the red bloods are cells. Some students went down the road of naming, the neutrophils and the leukocytes, the neutrophils, the basophils, the eosinophils, and you didn't need to do that. If you just say white blood cell, that's enough because all of them, the macrophages, the monocytes, the lymphocytes, the neutrophils, the basophils, the eosinophils, these are all white blood cells. Then the other type of cells that are found in the blood are the red blood cells. So red blood cells and white blood cells. Does that mean blood only has cells? Of course not. Blood has hormones, blood has water, blood has lipids, blood has sugars, blood has toxins, even toxins, metabolic waste. But when it comes to cells, that's what make the blood connective tissue. So today we're going to talk about the bone. So, we finished talking about cells. What cells are? Cells give us tissues. And, these tissues are going to give us organs, and organs are going to give us organ systems. So now we have four types of tissues. We have the connective tissue, and we have the bone tissue, and we have the nervous tissue. What's the fourth one? The one we did last week. Epithelial tissue. That's the fourth one. So today we're going to do the second type, the bone tissue. And we're going to leave the two friends for last. Because remember last week we said two types of tissues are friends. They're the same. They get excitable. But once they get excitable, they do different things. You get a paycheck, I get a paycheck. Both of us get paychecks. But do we spend them the same way? So the neurons get excited. The muscle cells get excited. But once they get excited, do they do the same thing? The neurons, when they get excited, they relay, they mediate information. While the muscles, when they get excited, they contract. But the other two, the one we did last week, the epithelial cells, they do not get excited. And today, the bone, which is one of the type of the tissues, the connective tissues, this one doesn't get excited. Does the blood get excited? No, only neurons and only muscles get excited. Okay, guys, so osteology is the study of the bone, the knowledge of, the study of. So please don't close it all the way. Thanks. So the ology is the science of, the study of. Osteo is the bone. So we don't say the bone system, we say the skeletal system. It is composed of bones, composed of cartilage and ligaments that are joined together to form the framework of the body. So before we get into the knowledge of and the study of the bone, we have to know that cartilage is the most important, most prevalent supportive tissue to the bone. Remember, we talked in the past about how the neurons in your brain, these neurons in your brain, they do not divide. They are terminally differentiated. They are in a state of terminal senescence and quiescence, but there are supportive cells. You know, no tissue stands on its own. Every tissue needs supportive tissue to help it survive. So, and remember we said that, you know, in the in the brain, even though these neurons they do not divide, we still get brain cancer. So why is it the case that we get brain cancer even though the neurons they do not divide? Then we agreed that it wasn't the neurons who underwent the cancer. It was the supportive cells to the neurons that underwent the cancer, and cancer spread, metastasis spread. The cancer spread from these neurons. Please don't close it all the way. Yeah, just somebody's coming. So there's a shift. So there is cancer invasion and cancer metastasis. So we're going to metastasize from the supportive tissue to the main tissue. How do we say main tissue? Parenchyma, parenchyma. So when I tell you what is the parenchyma for the nervous tissue, that's going to be the neurons. The neurons are the parenchyma for my brain tissue. Same thing with my bone. What is the parenchyma for my bone? These are the osteoids. These are the bone cells. But like we said, no matter what tissue you're looking at, you can never stand on your own. You need supportive tissue. So who is the supportive tissue that helps the bone stand on 2 feet? Is the cartilage. The cartilage. The muscle is a separate system. But we're talking within the system. The bone tissue is supported by the cartilage. And you know, we will learn that we have ligaments. These ligaments, they help attach bone to bone. They help attach the bone to the bone. While the tendons, they help attach bone to muscle, or muscle to muscle, or valve to muscle when we do the cardiovascular system. And you must also be very aware. You know, last week we talked a lot about keratin. And we said, you know, proteins, it depends. Some proteins, you know, like the people, some job you need to have secondary school, you're done. You don't need more than that. Some job you need college, associate. Some job you need bachelor's. Other job you need master's. Then other jobs you need doctor. Other job you need postdoctor. So we said that keratin is what's the structure? What is the structure of keratin? Keratin. What structure? You know, proteins, they are in the shape of primary structure, secondary structure, tertiary structure, and quaternary structure. So what is the shape? No protein is functional. No protein is ever functional at the stage of primary. No protein is working as a primary. Primary is like elementary school. So no protein is working as primary. The earliest you can work, the earliest you can be a functional protein is secondary. So what is the function of primary? Primary structure is the nascent transcript. So that is the transcript that tells you, what is the structure of the protein. So for example, hemoglobin, the nascent primary structure is going to say hemoglobin gotta be quaternary. So hemoglobin is going to fold upon itself using hydrophobic effects, ionic interactions, and you know, all of these disulfide bridges to make a quaternary structure. So we said last week that keratin is what structure? Secondary. So keratin will do the job at secondary. So if you fold it back to first degree, that's primary, and you give it the proper pH, the proper temperature, it's gonna fold to secondary, it's gonna do the job. So is collagen. So is collagen. Collagen does not need to be tertiary. Collagen does not need to be quaternary. Collagen, if it's secondary, it'll do the job perfectly. So now we're gonna see that collagen is the most prevalent protein in the body. There is more collagen than there is hemoglobin. It is the most prevalent. What is the most prevalent population in the world? What is the most prevalent population? Who are the people who are the most on Earth? There's 7 billion people on Earth now. Who are the most? I think it's China, not India.
It's China.
It's China. So who's the most now in protein in the body? Who is the most? Collagen. Collagen. Hemoglobin comes after. So hemoglobin is like India, but the China is the collagen. Okay. So what are the functions of the skeletal system? And if you say support and movement, that was elementary school. You know, they teach the skeletal system in elementary school. In third grade, this is the bone. Why do we have a skeletal system? So we can walk. If you put on the exam, the skeletal system is to support and movement. That would be the same answer that somebody right now is taking the skeletal system in third grade. Now we're gonna learn something more than walking. Who thought that the bone is responsible for blood? You know, your blood come out from your bone. So we have the red bone marrow and we have the butter, the yellow bone marrow. So if you slice, remember when we were doing the histology, we said you slice the bone in half, you're gonna see that there's yellow marrow there because that tells you that you need a lot of fuel, we need a lot of power because this bone is moving a lot and this bone is the site of a lot of activity, so it needs a lot and a lot of energy. Also, the bone tissue. You know, whenever you are examining a tissue, you should always be preoccupied with what? Is it dividing or not? That's a big issue. Last week we talked about epithelial tissue. Is epithelial tissue dividing tissue? What did we say last week? Is epithelial tissue dividing tissue? Does it divide? Does epithelial tissue enter the cell cycle and divide? Or does the epithelial tissue terminally differentiated or locked in a particular senescence, replicative senescence?
It don't divide.
It divides. That's why when you scratch yourself, it's not gone. It can come back up. It is your brain that is terminally differentiated.
Yeah.
That is terminally differentiated. And so is the bone, is like your epithelial tissue. It divides. That's how when you break a bone, you have a bone fracture, the bone can heal. But if you have brain damage, it cannot heal. All this Parkinson, all these boxers, they get punched in the head, that region is damaged, is never coming back again. But your bone, if it's broken, it can come back again. Now, the second thing we need to know is that your bone is like a mountain of salt and minerals. Your bone is rich in calcium. Your bone is rich in phosphate salt. So that's important for calcium homeostasis. If calcium drop in your blood, remember we said we are preoccupied with restoring hypo and hyper to you. So if you have hypocalcemia, we go to the bone, we degrade the bone, we scratch the bone, we liberate from the bone powder, and that brings up the calcium level in the bone back up. If we have too much calcium now in the blood, then that's a problem. Then we do the opposite. We take calcium powder from the blood and we dump it like mud on the mountain of the bone to make the bone density higher. So the ability to shift back and forth based on the metabolic demand, our ability to have homeostasis, calcium homeostasis that is central to the bone. So the bone is not just for walking. The bone is not just for walking. Somebody who cannot walk, somebody who is paralyzed, still using their bone. Somebody who is not walking with their feet, somebody who is paralyzed, still using their bones and the feet to make blood. Still using the bones and the feet to make calcium. Still using the bone and the feet to make phosphate. Also, the bone is important because what is phosphate also good for? The pH balance. The pH balance. So your bone is sometimes like your kidney. Your bone is like your kidney because your bone is able to regulate. Your bone is able to regulate if the pH level went to acidosis, it will buffer that. It will use phosphate as a buffering system. And blood formation. So the red bone marrow makes for us red blood cells. But does the bone marrow only make red blood cells? White blood cells are not made in the bone? They are. They mature elsewhere, but they are made in the bone. You cut your foot cut is gone, you're gonna drop the amount of white blood cells in the body because they are made there. And we will learn in the immune system next semester that the white blood cells, the T cells, some of them, they mature in the thymus. That's why they call it the T cell. So they come from the bone, but they mature in the thymus. You're born in Jamaica, but you mature in the US. So then they born in the they born in the bone, but they mature in the thymus. But the B lymphocyte, they are born in Jamaica, they grow in Jamaica. So the B lymphocytes, they are born in the bone marrow and they grow in the bone marrow. That's why they call them B lymphocytes. And then you have to lastly understand that the bone tissue is important for secreting hormones. So you have to understand that the bone cells secrete hormones that affect, insulin, and they moderate the stress response. So you see, this hormone erythropoietin. So erythropoietin is secreted from the kidneys after it was sensed that there is a drop in oxygen level, and then that would communicate between the kidney, the urinary system, and the bone. So if you look there, you will see that also the protection. Your bone, you put the money in a safe. You put the money in the safe so nobody can break it and take it. So all of the visceral tissue, your heart, your liver, your lung, your brain, that's very important. I mean, you can lose a leg and survive. You can lose an arm and survive, but you cannot lose a brain and survive, and you cannot lose a kidney and survive, and you cannot lose heart and survive, and cannot lose liver and survive. So all of these important viscera are always in a case. So you see a cranium, that's the case that covers the helmet that cover my brain tissue. The rib cage cover my heart, my lungs, my pancreas. Okay, my bladder, my genitalia is covered with my pelvis. So you see, all of these are the functions of the skeletal system. Only one of them is the support and walking and the movement. So that shows you we only knew the tip of the iceberg, for the skeletal system. So for the skeletal muscle, the skeletal system, and sometimes we say it with the muscular system because we already said last week that the bone, you cannot move the bone unless you pull a rope. So the rope is the muscle. So the muscle pull the bone, and the nerve stimulate the muscle. So it is the nerve who depolarize the muscle. The muscle will contract. When the muscle contract, it'll pull the bone. So somebody who's paralyzed have no problem in the bone. They have no problem in the muscle. They have problem in the nerve. They have problem in the nerve. So when they do the stem cell, the stem cell, and they plant nerve stem cells, then the stem cells are going to be able to restore for them the ability to walk. Okay? Any question? Okay. So bone is a very hard and a calcified tissue. The bone is a very hard and calcified tissue. So this bone, as we said, is the site where we are going to synthesize the calcium when we need. It's going to be the site where, so we begin with general. We begin with general, and then we narrow down. So if we want to know the properties and the functions of the skeletal system, you begin with the most basic. You begin in priority. What is the most basic function of the skeletal system? We mentioned the support. This is the one that we knew most basic. I mean, without our skeletal system, we will not be able to walk for survival. You know, survival. This is one of the initial, most prominent properties of the skeletal system is to help us survive threat in a fight or flight. And we said that the skeletal system is important for providing the case, is the safe that protects the important, you know, you put the money in the diamond and the silver in the case. So you put your brain, your pancreas, your kidneys, and your liver surrounded always with the rib cage and with the pelvis, the genitalia for reproduction. So reproduction is important. You need to protect the genitalia so they are encapsulated with this girdle, the pelvic girdle. We said also for movement and breathing. So, you know, we rely on the intercostal and extracostal muscles that stretch the rib cage. Rib cage is bone, right? The rib cage is bone. So we stretch, we increase the transverse diameter of the rib cage to accommodate a lot of air in the to accommodate a lot of air into into the to accommodate a lot of air into the lung, and then we expel all of the air. We utilize the diaphragm, and then we contract the intercostal muscles to expel the air out. And we said that the bone tissue is a bank for calcium salt, a bank for phosphate salt, and for to restore calcium homeostasis. And we said, you know, calcium has to be in balance because too much calcium is going to turn on an enzyme that's supposed to be off. You know, sometimes the autocatalytic destruction of the pancreas is caused by excessive calcium. So that's why we use our bone as a mountain. We dump all of the extra calcium, the excessive powder calcium into the bone tissue, and vice versa. You know, we said we are preoccupied with restoring hyper down to U and hypo. We bring it up to U. So we don't want hypercalcemia. We don't want hypocalcemia. We want eucalcemia. So if we have too much calcium, we have proper hormones that are going to bring down calcium to the normal homeostatic range. And if we have too little, we're going to degrade the bone. We're going to crush down the mountain and bring down powder from the mountain. Also, not just calcium salt. What are the other types of salt that we have in the bone besides calcium? Phosphate, excellent. So this phosphate is very important for phosphate homeostasis. We have we don't want hyperphosphatemia, hypophosphatemia. What is the usefulness of phosphate? I'm sorry, say what's that? pH, very good, excellent. So phosphate is a buffer. So you know we don't say phosphate is more for pH. We say phosphate is a buffer. So phosphate regulates intracellular pH. Extracellular pH is regulated with bicarbonate. Bicarbonate. That's the buffer that regulates the pH outside the cell. But the pH inside the cell is regulated by the phosphate. And you know the remember when we did the histology, we said we have different histological planes. We cut the bone tissue transversely. We cut the bone tissue coronally and sagittally. We said the boiled egg, if you don't cut it in half, you will never know there is a yellow yolk inside. So there is red There is red bone marrow. If we didn't cut it in half, we would have never known that there is red marrow there. In addition to red marrow, what other color marrow found in the blood?
Yellow.
Yeah, the yellow marrow. So this yellow marrow signifies what? Yeah, the fat. Excellent. So if I have a lot of fat, excellent. So fat, butter. So yellow marrow, butter, fat. So why do I have a lot of yellow? So you know everything for a reason. So there is a reason why there has to be a lot of fat in the bone. So why is that the case? Speculate. You know, this is not a right or wrong answer. So as so for cushioning and because there is a lot of demand for movement. I need to metabolize a lot of fat to ATP. And fat, as we will learn metabolism, we will see fat is our best source for ATP. And what's the name of the hormone that is secreted by the kidney and will immediately stimulate the bone marrow to increase the genesis and the making of? Erythropoietin. Very good. You guys doing too good today because Dr. Paul here. Okay. Okay, wow. Okay. All right. So bone tissue is hard calcified tissue. I promise you, I will ask you on the exam, what is the name of the material that caused this bone tissue to become hard like rock? It's called, no, collagen is for the ligament. Now imagine your bone ligament is so tough. You will not be able to bend your, yeah, so it's hydroxyapatite. Hydroxyapatite. You know I'm gonna change the name hydroxyapatite, hydroxyporapatite, hydroxyapatite. I'm gonna change the name. So you have to really, this is high yield. Hydroxyapatite is what causes the bone to become like rock. So this mineralization, the bone becoming the bank very rich in all of these mineral salts and electrolytes. That's what's gonna harden the bone. So when we look in the lab, when we look later on to the structures of the bones, you will see that these bones, they do not all look the same. Some of them are flat bones. Some of them are long, meaning that they are long more than they are wide. And you have the tiniest bones in your body versus the longest, biggest bone is your femur. Now, who's gonna tell me the smallest bone for extra credit? For one whole point on the exam.
That's right. It's
In the wrist. Good try, but wrong answer. In the ear. But what is it called? The ossicles. The ossicles. So they come three. So that's one third. One third. So they come as a team. So, but very good, excellent. So okay, we will sort that. We will sort that. We will sort that out. So we have flat bones. We have long bones. So when we have a flat bone, when we have a long bone, why is there a variety in the morphology or the shape of the bone? Why is that? Why is that the case? For the function, excellent. So if there's a flat bone, that shows you it must be flat in order to perform a function that requires it to be in that shape. So you'll see some bones are thin, curved, um, plates, and they protect the soft organs. So for example, you have to know at least three examples of flat bones. And an example of that is the parietal bone. Parietal bone, these are the two side bones that are in the skull. And the sternum. The sternum, this is the bone that is right at the center, connecting the rib cage, the bones of the rib cage from both sides. And then the scapula. That is the shoulder blade. The scapula is the shoulder blade, and the ribs and the hip bones. So these are the flat bones. We will look at them in lab today. We will touch them. So in the mod, there's in the room, right? So we will get that from there. And then these are the long bones. These are the ones that you know. And by the way, the laterality is very important. So on a lab practical, if there is a humerus and I ask you what is that, and you say that is the humerus, this is incomplete because the right humerus versus the left humerus is a big deal. Imagine you have a surgery, and you know instead of doing it on the right humerus, they do it on the left humerus. So it's gonna take some skill to for you to be able to tell right from left. So like I said, you always begin with the most major thing. When it comes to anatomy and physiology, you have to know the big picture and then you narrow down. You know, you can't know the small street, but you don't know the PQE or the Major Deegan Expressway. You don't know the big highway, but you know the name of the tiny street. So when you want to know the bones, you begin with the biggest bones first. You got to know where your femur is. Okay, you have to know where your radius is. You have to know where your ulna. You have to know the fibula. So always begin with the widest. Remember the pyramid. We begin with the most basic, then you narrow up. But you don't start memorizing the little nerves and the little vessels and the little bones and you move up. No, you begin from big and then you narrow down. And it's also very interesting that some bones they cannot be classified into black and white. Are you flat? Are you long? Are you short? No. Some of them, they are irregular bones. So these are short bones, approximately equal in length and width. Okay. Um, Okay, so we have compact bone, and we have spongy, and spongy bone is interesting. You know, you look at the sponge, you wash the sponge that you will use to wash the plates. So it's full of pores, full of holes. So that is the spongy bone, and that is the bone that gets the osteoporosis. You know, the senile osteoporosis for men and the menopausal osteoporosis for women. You know, when there is a menopause and a deficiency in the level of estrogen, that estrogen is important for bone density for females. I mean, estrogen is the essential hormone for female. They call it essential because it gives the essence of a female. What is the essential hormone for male gives the male the essence of the male, the voice and the testosterone. So people assume that it's only women will have the menopausal osteoporosis because they have a deficiency of estrogen, but men also, as men get older due to the loss of estrogen. What's the name of male related osteoporosis that is associated with testosterone deficiency? Andropause. That's interesting. But what did I just say? The one I just said, begin with an S. Senile osteoporosis. But that's interesting. Maybe I gotta look into that. Andropausal menopause. Maybe I didn't come across that one, but that's interesting. Very interesting. Okay, so then we're gonna look at the structure of the bone. So this is why this lecture is very special because we need to have an on-hand experience with recognizing the diaphysis and the epiphyseal plate. So the epiphyseal plate is a remnant of the childhood growth zone, and the epiphysis is the enlarged end of the long bone, and it strengthens the joint and anchors the ligament and the tendon. The diaphysis happens to be the shaft that provides this leverage. Okay, so we have to recognize that cartilage is what gives our bone its tensile integrity, and it has a layer of hyaline cartilage that covers the joint surface and allows the joint to move freely. So one of the biggest problems that come with bone pathology is the restricted range of movement. So this is hardening in the hairline cartilage, and that comes with arthritis. So our inability to properly move and rotate our joints. The nutrient foramina. These are minute holes in the bone surface that allow the blood vessels to go through. So you know the bone tissue, we said it's rich in fat and rich in lipid because it needs to make a lot of ATP, but also it's invigorated with a lot of red blood cells because what did we say the bone is a type of? Is it a type of a tissue that goes into the cell division cycle, or is it a terminally senescent, quiescent type of tissue? Yeah, so it divides a lot. So if it's gonna divide a lot, it's gonna need a lot of blood. It's gonna need a lot of cytokines to stimulate it to enter the cell division cycle. We're going to also need nerves also. So one of the videos that you guys had to summarize was the healing of the bone fracture. So how does it happen? You learn that when the bone breaks, it wasn't just the bone. It was the bone, the nerves that go inside the bone, that the blood vessels that go inside the bone, and you see a lot of blood clots making like a cushion or a blood tumor around the bone. So that shows you this bone tissue is going through this nutrient foramina, is invigorated with a lot of blood vessels because the bone tissue needs nutrition. Okay, so this here shows us the anatomy of the long bone, and that shows us the in the medullary cavity, we're going to have our yellow marrow, and the red bone marrow is found in the epiphysis, and you see that there is multiple layers and sheath that wrap around multiple layers and sheath that wrap around the bone tissue, in which to provide insulation, to provide this structural support for all of the blood vessels that are going through and invigorating this bone tissue. So you see that there is a layer of articular cartilage, and that is what enable the this ball and socket joint, that the hip joint that enables you to move and walk. And you know, as we get older, there is a deterioration. There's a deterioration in the articular cartilage. Yes. Yeah.
So is it the inverse? Is that
So, do you mean is this the right femur versus the left femur?
right? So the license is pointing towards the direction of the femur.
So the epiphysis is the anatomical region. So this top region here, from this, the diaphysis ends at this region. So this is the diaphysis. Above the diaphysis, the terminal ends of the spectrum of the bone, this is the epiphysis. So that is the region where we have the red bone marrow.
Right, I would say based on the question you said before, that may or may not be on the test.
Mhm.
So it's pointing, so for example, this epiphysis is pointing to.
You're right, exactly.
So this epiphysis is pointing to the exactly the right. So you have to So this is the
So would that be the left or the right?
that's the right, and that is the left femur.
Depends on your position.
That's what
Okay, so that type of question, you would have the actual bone in front of you. So you'll not have a picture. You will have the actual bone. So the first step you will have to do is put yourself in the anatomical position. So you put yourself in the anatomical position, then you will be able to tell, yeah, right from left. So if you look at this bone right now, the one I'm pointing with my mouth. This one is, this is the ball part of the joint, and the socket will be on the top. So this is the, according to the anatomical position, that is my right femur. That's the right epiphysis of my right femur, and that is the left epiphysis of my left femur.
So in summary, a shortcut to find out if it's the right or left is to look at the direction of the epiphysis.
Is to put yourself in the anatomical position, because I can put it upside down. So you have to master the skill of the anatomical position. So remember, we mentioned how to align yourself properly with the plane of the anatomical position. So when I say the right ventricle, the left ventricle, the right atria, the left atria, I'm not talking about your right atria, I'm talking about the anatomical position when the cadaver or when the model is in the anatomical position. Okay, so you place this epiphysis that you're looking at now in the anatomical position. So now I see an imaginary skeleton that is looking at me. So now I'm looking at the dead cadaver, and that the dead cadaver is laying down, and now I can see that like this. So now I am the dead cadaver. You see? So this is my right femur.
It's opposite to you. It's opposite to you.
You know, but you can't look at it that way, because you can go behind the anatomical
Well,
position.
yeah.
Yeah, so it is never about you looking at it, it's about the anatomical position. So you just have to place it in the anatomical position. You can go behind the anatomical position, you can go in front of it, you can go to the right of it, you can go to the left of it. But the most important thing is you put the bone of interest in the anatomical position. You can be looking at it, you can be facing it. So now look at me. I'm right now superimposed with this gray one, with the right epiphysis of my right femur. We're facing that way. Now, if I turn this way, it's still in the anatomical position. I'm just facing I'm 90% facing it. I'm 90% facing the other position. Is that clear?
Yeah.
So it's not you. So it's nice. You know, it's always you trying to find a way to make it easier for you
To the point of view.
point of view is up to you. But it is always you have to put in the anatomical position. Okay? So all the descriptions are based on anatomical position. Okay, so that is so this is the anatomy of the long bone, and this is the okay. So now let's look at the compact bone, and let's look at this is the trabecula, and this is the okay. So now let's look at what kind of cells do I have. You know, I mentioned earlier that we need to have bones, that we need to be able to build bone. Remember, did you do the video? The video told you osteoblast B build, osteoclast C cut. Yeah, like a jackhammer. So I'm trying to put the letters together. So osteoclast, cut. It cut down. Resorption. Osteoblast, B, build up. Very good. Okay. So osteocytes, these are former osteoblasts. They retire. So osteocyte is the osteoblast that retire. The osteoblast build up a lot of bone. It reached a layer where it stopped. Students used to have a problem, you know, the difference between lacunae and canaliculi. You know canaliculi from the name canal. That's why they call it canaliculi. Canaliculi is a canal. So that canal is going to connect the lacunae. The lacunae are the tiny cavities where the osteocytes retire. So you know the nursing home? So osteoblast build up bone is gonna retire. What's the nursing home, the retirement home for the osteoblast? The lacunae. The lacunae. The lacunae are the tiny cavities where osteoclasts retire. Then the osteoclast, for them to get the nutrition, these are little channels that they connect the lacunae. They connect the lacunae. So the cytoplasmic processes of the osteocytes reach into the canaliculi and contact the processes of neighboring cells. So there are gap junctions that allow for the passage of nutrients, waste, and signals. So some osteocytes reabsorb bone matrix while others deposit it. So they act as a strain sensor. When stressed, they produce biochemical signals that regulate bone remodeling. Okay, four types of bone cells. There are the osteoblast and osteocytes. Osteoblast and osteocytes. They secrete the hormone osteocalcin. So you know that from the prefix osteo. Osteo, that is bone. So osteocalcin, that is liquid tissue that is gonna later harden up and become bone. So we harden up on stages. So part of the body's acute stress response, they stimulate the pancreatic secretion of the insulin. It increases insulin sensitivity and promotes energy availability. That was a really nice input. That androgen menopause. Never heard of it. Interesting. Yeah, I never did. I need to go back to the books.
Yes.
Yeah, my books are too old now, apparently. Where did you get that from? You read that in Saladin? From where? From the from the work hospital?
No.
Okay, good. Where was that? PubMed. Saunders? Is that an anatomy physiology book?
It's in the, if you did the MPN program, it's in the book.
So let me go activate the ATI, and we're gonna do some ATI. How about you guys gonna miss out on all the?
We know it. We'll figure it out.
Okay, maybe next semester. Okay, so remember, what do the osteoblasts become when they retire? Osteocytes. Very good. Okay, so these are the osteogenic cells, the osteoblasts, and these are the osteocytes. You know, next week is the exam, so you got to go do that lab homework exam so you can come next week do really well. You know, if you're just gonna come one time, take notes, take photos, and you go home, you don't review until you show up next week, you're not gonna do well in the course. I promise you. This course need a lot of reviews, a lot of reviews.
Are you gonna set up the lab study guide?
Okay, yeah, I'm gonna send you the lab study guide, but you don't have to submit it. Just yeah, so just use that for just use it for so now you only have to submit the summary, the video summary, but not the study guide.
Is lab is going to be just like 1% and other not on.
Not just like it. There's gonna be modification, yeah. It's gonna be, I'm sorry? 50 questions, yeah.
Like the homework.
50 times 2, 100. Yeah, so you got to study the homework, but not just the homework. The homework, the study guide, the summaries. So you're going to have both figures and concepts. Okay? Okay. Okay. And we may have the bone. So we have like the femur. We're going to have you got to know your bones. So when we do the lab later, so you know, you see a picture. What is that? So the first thing, like I said, begin basic. Identify, that's my femur. Then move on to, is it my right or my left? Okay, you're going around memorizing the really tiny, small bones in the ear, and you don't know the huge femur. Unbelievable. I had a couple of students like that. A couple of students, they know the common carotid, they don't know the aorta. They don't know the brachiocephalic trunk, and they know the common carotid. It's like you know you don't know the FDR, but you know some street here. You know Madison Avenue, you don't know the FDR. So always begin with the biggest and you narrow down, because that's what they're gonna ask you on the NCLEX. So begin with the biggest and move on. There we go. What is the matter that I told you that makes the crystallized bone really? Hydroxyapatite. That's 85. That was on the video too. So it showed you that this is the material that is very strong. So these videos are important because all these homework questions, they're on Quizlet. They're on Quizlet and people sending them in the group chat is really doing the homework is no assessment to your learning. It's sitting down and watching these videos and summarizing them. That's what's going to reinforce that you are learning and you're going to get the points for. Okay. Okay, so I'm taking me a lot of time. I'm reading, but the people that I assigned the 5 pages, they did some Googling. You think I can't tell what I made the video, I know what I talked about, and you Google some stuff, you put it there, I never talked about it, you're gonna get 0 for that. Okay? No, yeah, the assignment was clear. You had to summarize my key concept. We said that in the beginning of the class. No problem. I'll give you a second chance. I'll reopen it. But if you go around Googling stuff, copying and pasting and Googling stuff that somebody put something about I never talked about, it was there. Don't research nothing. Just what I say, type that. That's it. Okay? If you want a research project, I'll give you one in the end. But, no, that's not plagiarism. Yeah, it's not plagiarism. No.
No, but you write what he said. You don't want.
That's for my assignment.
Yeah. But that's no, because that's right. But
Yeah. Okay. So what's the name? Guys, what is the name of the material that is responsible for the crystallization and the hydroxyapatite? So now this matrix always means what? Extra. So always come with X. Matrix X, extracellular X. So that's how you make a connection between them. So collagen and minerals of bone form a composite material that provides flexibility and strength. The mineral portion allows the bone to support the body weight without sagging. So rickets is a disease caused by mineral deficiency and resulting in soft, deformed bones, also known as bowed legs. So the protein portion gives more flexibility. So collagen molecules contain sacrificial bonds that break under stress and dissipate shock under the load. So osteogenesis imperfecta. What is osteogenesis imperfecta? That is brittle bone disease. It results from a defect in the collagen deposition. Defect in collagen deposition. Compact bone. So the histology of a compact bone is we have the concentric lamella. These concentric lamella are layers of matrix surrounding a central Haversian canal running longitudinally. So there's a central canal and it's the lamella. It constitutes this is a constituent that is made up of lamella and osteon. This is known as the Haversian system. The central canals connect by transverse perforating canal. Soda is the leading cause for bone disease and is dangerous, especially the Coca-Cola. It causes the breakdown of bone tissue, especially in the male or female. Coca-Cola, male or female. Yeah, they're gonna pay the price later. That's pomegranate juice. Okay. Okay, so you gotta go do that. Begin, like I said, begin with big, narrow down. Begin with that. Begin with that. Um, lab homework exam. Always do the lab homework exam, then the study guide, then the video summaries. Today I had one student, one of my best students, didn't do the homework. She did the video, she did the something else, and she didn't do the homework, and she did bad on the exam. And somebody else, they did really well. They did the home. So the homework is the most important. So please make sure that you do that. Okay. That is the compact bone. Spongy bone is always in the middle. Spongy. You see the sponge? If you look at the bone, when we look later, you see that in the middle it has holes, and on the sides it has this compact structure.
That's the bone marrow.
Yeah. This is now let's look at the histology of osseous tissue. Histology of the osseous tissue. So that is my osseous tissue. And you see there is a lot of nerve, there's a lot of blood vessels through the bone. Just like the building, it looks like it is made of brick, but through the brick system, what do you have? You have blood, you don't have blood, you have
steel.
through the, you don't have steel, you have
Cement and steel goes.
yeah, so the cement is the strong. Through the cement, what do you have? Pipelines of what? Plastic, water. You have also electricity wires going through. Okay, and you have the heater and the AC. So the same thing. That's gonna go through the bone tissue. So the spongy bone, that's why they call it spongy. It's spongy because it has holes in it like a sponge. So the lattice of bone slivers, these are known as the spicules and plates, trabeculum. They are covered with endosteum. There's a sponge-like appearance where spaces are filled with red bone marrow, and matrix is arranged in a lamella, but few osteons and no central canals. All the osteocytes close to the bone marrow, they provide strength with minimal weight, and the trabecula develop along the bone's lines of stress. The spongy bone structure in relation to the mechanical stress. Now the bone marrow. So now we are moving in from the compact bone. Who's at the surface? The most surface. That's the compact bone. So the hydroxyapatite is all over the bone, whether spongy bone, whether compact bone. Even the building. Where do you find the hardest cement? On the outside or in the middle? Or in the middle? Is this wall as hard as the one that's on the very outside?
No.
No. Same thing here. So the bone, the very outside is the toughest. And then you get more softer and softer as you move to the center. So the bone marrow is a soft tissue occupying marrow cavities of the long bones and small spaces of the spongy bone. There's red bone marrow, that is myeloid tissue. Red bone marrow is a myeloid tissue, including hematopoiesis that produces blood cell. In nearly every bone in a child, in adults, found in the skull, the vertebra, the ribs, the sternum. Part of the pelvic girdle and the proximal heads of the humerus and the femur. So the yellow bone marrow is found in adults. So you have fatty marrow that does not produce blood, and it can transform back to red marrow in the event of chronic anemia. adult distribution of the red and yellow bone marrow. You see red bone marrow, it shows you where is it found, and this is yellow bone marrow. Now, how does bone develop? The genesis, the genesis of bone tissue, or the ossification or osteogenesis. So is the formation of bone. So ossification, osteogenesis, tomato, the same thing. If you hear ossification, say we never heard of that. We only studied osteogenesis. Or you hear osteogenesis, say we never heard of that. We only studied ossification. They are the same thing, which is the process of the formation of the bone. So bone develops by two methods, both beginning with obviously the mesenchyme, the mesoderm. So there's embryonic mesenchyme. There is intramembranous ossification, and there is endochondral ossification. Now, intramembranous ossification. What's the difference between these are the two types that we develop with. Intramembranous ossification, and then there's the endochondral ossification. The intramembranous ossification produces the flat bones of the skull, the majority of the clavicle, and part of the mandible. So what are the stages of intramembranous ossification? The first stage is the deposition of the osteoid tissue into the embryonic mesenchyme. So when we deposit osteoid tissue in the embryonic mesenchyme, there is a calcification of the osteoid tissue and entrapment of the osteocytes. The first step is the deposition of the osteoid tissue into embryonic mesenchyme. Yes, you had a question? You said something.
I said fluid. I was just saying fluid.
Fluid? Mesenchyme, yeah. So the first step in intramembranous ossification is the deposition of osteoid tissue into embryonic mesenchyme. The second step is the calcification of this osteoid tissue and entrapment of the osteocytes. Okay, then we entrap the osteocytes and retire them in that osteoid tissue. Then a honeycomb of spongy bone with developing periosteum. Filling of space to form a compact bone at surfaces, leaving spongy bone in the middle. So intramembranous ossification also important in lifelong thickening and remodeling of the long bones. So you see, this is the intramembranous ossification. It begins with the deposition of osteoid tissue. You see, this is the osteoid tissue. The osteoid tissue into the embryonic mesenchyme. Okay, that's the first step. Then the next step, after we deposited osteoid tissue in the embryonic mesenchyme, there's a calcification of the osteoid tissue and entrapment of the osteocytes. So you see the osteocytes are now beginning to appear, and they are going to drown. They're going to get frozen. They're going to get frozen up and retired in there in this calcified osteoid tissue. Then the third step is the honeycomb of the spongy tissue with developing periosteum. This is a honeycomb of the spongy bone with developing periosteum. There is a filling of space to form compact bone at surfaces, leaving the spongy bone in the middle. Okay, this is the blood vessel. That is the osteoid tissue, and that's the first step, deposition of the osteoid tissue. This is really important. How does intramembranous ossification unfold? The first step is you need that matter You need that dough that you're gonna cook into cookie or pancake or cake. That is the osteoid matter, the osteoid gooey liquid that's gonna harden up later into the embryonic mesenchyme. So it was deposited first, the osteoid tissue was deposited, and then you would have the entrapment, you'd have calcification of the osteoid tissue. Now the osteoid tissue is going to harden up, it's going to get cooked. So now it is no longer soft dough, it's going to be now very tough cookie. And then there's a calcification of the osteoid tissue, and then the osteocytes are going to retire there. They're going to be entrapped. And then there is the honeycomb of spongy bone with developing periosteum. You see, there's a honeycomb of spongy bone with developing periosteum. See, that's the honeycomb of spongy bone with developing. This is the bone trabecula, and this is the periosteum. The periosteum begins to develop, and that's the mesenchyme. In the middle, you have the spongy bone. Here, you had no spongy bone. Then you had the honeycomb of spongy bone with developing periosteum. And lastly, you have filling of space to form a compact bone at the surfaces. That's why we said compact bone always at the surface, because it's the strongest. It's not in the middle. It's not spongy bone is in the middle, soft. But the harder bone is all the way on the outside. Okay. You see that shows you the periosteum has a fibrous layer, osteogenic layer, osteoid tissue, osseous tissue. And you must always recognize, you said osteocytes, they retire. But who are osteoclast and who are osteoblast? Osteoblasts are important for building up, and osteoclasts are important for good, cutting and breaking down. Excellent. So that was intramembranous ossification. Now, this is not the only way that we make osteogenesis by intramembranous ossification. The second way is the intrachondral ossification. In intrachondral ossification, the bone develops from hairline cartilage model. It produces most bones of the body. These are bones of the limbs, the vertebra, the ribs, the sternum, the scapula, and the pelvic girdle. This is bone that developed from hairline cartilage. So intramembranous ossification develops from the mesenchyme. Remember? Developed from the mesenchyme. Intramembranous ossification develops from the mesenchyme, while the intrachondral ossification does not develop from the mesenchyme, but rather develops from the hyaline cartilage. This is golden. This is money. Knowing the difference between osteogenesis of the intramembranous ossification and endochondral ossification. Intramembranous ossification is from the mesenchyme. That's why the M with the M. Intramembranous ossification, mesenchyme. While the other one, endochondral, there's a H in there, endochondral. There's a H in there, endochondral meaning hyaline cartilage. So the stages are the mesenchyme forms early hyaline cartilage. Then there's a formation of a primary ossification center with a bony collar and periosteum. There's vascular invasion and formation of primary marrow cavity and appearance of secondary ossification center. And the bone at birth joins the enlarged marrow cavity and secondary marrow cavity in one epiphysis. In the endochondral ossification, the fifth step is the bone of the child is going to contain the epiphyseal plate, and the adult bone contains a single marrow cavity and close an epiphyseal plate that becomes an epiphyseal line. There you go. These are the stages of the endochondral ossification. What was the first step? There is an early cartilage model where the mesenchyme is going to make hairline cartilage. What does hairline mean? Glass, 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 glass shape. So the formation of, then there would be a formation of primary ossification center, bony collar, and periosteum. And there's a vascular invasion where there's a formation of primary marrow cavity and appearance of secondary ossification center. Then there would be bone at birth with enlarged primary marrow cavity and appearance of secondary marrow cavity in the epiphysis. The bone of the child with the epiphyseal plate at the distal end, and the adult bone with a single marrow cavity and a closed epiphyseal plate. See, there's the formation of the primary ossification center with a bony collar and periosteum. Then there is a vascular invasion with formation of primary marrow cavity and appearance of secondary ossification center. Then the bone at birth with enlarged primary marrow cavity and the appearance of a secondary marrow cavity. Then the bone of the child with the epiphyseal plate at one distal end. You see the epiphyseal plate. And finally, the adult bone with a single marrow, no secondary centers, and closed epiphyseal plate. You see, intramembranous ossification happens in the brain somewhere, while the endochondral ossification must happen elsewhere, like in the clavicle and the femur. Bone growth and remodeling. So ossification continues throughout life with the growth and remodeling of the bones. So there is bone elongation. So the ossification continues throughout life with the growth and remodeling of the bones. So there is bone elongation where there is epiphyseal plate that serves as a growth zone. There's a transitional zone on each side where cartilage replaced by bone is called the metaphysis. That's very important to know. The metaphysis or the metaphysis is the region where you would have a transitional zone where cartilage is going to be replaced by bone. That's the metaphysis. So the epiphyseal plate is going to be the growth zone. And there's a transitional zone where cartilage is replaced by bone. So the structure of the metaphysis corresponds to steps of cartilage replacement. There's the zone of reserve cartilage, there's a zone of cell proliferation, there's a zone of cell hypertrophy, zone of calcification, and zone of bone deposition. So the x-ray of a child's hand, you see, that shows you the diaphysis, the epiphysis, the epiphyseal plate, metacarpal bone. That's an epiphyseal plate, and that's another epiphyseal plate. So that shows you the zone of reserve cartilage. That is a typical histology of resting hyaline cartilage. Then the zone of the cell proliferation, you would have chondrocytes. Chondrocytes do what? Chondrocytes. Cyte is a cell. Chondrocytes, meaning what? They make cartilage. Cartilage forming cells, chondrocytes. If you're a chondrocyte, you make cartilage. Multiplying and lining up in rows of small flattened lacunae. The zone of the cell hypertrophy is a cessation of mitosis and enlargement of chondrocytes and thinning of the lacuna wall. The zone of calcification is temporary calcification of cartilage matrix between columns of the lacunae. There is a zone of bone deposition where there is breakdown of lacuna walls, leaving open channels, death of chondrocytes, bone deposition by osteoblasts, forming trabecula of spongy bone. Bone elongation. Bone elongation manifests when we have growth in height. So chondrocyte multiplication in zone 2 and hypertrophy in zone 3 push the zone of reserve cartilage toward the end of the bone, and the bone is going to elongate. So cartilage growth from within is called interstitial growth. Cartilage of the epiphyseal plate is depleted by late teens, early 20s. So primary and secondary marrow cavities unite into one cavity. The junction is filled with spongy bone, and that's the site of original epiphyseal plate. It is now the epiphyseal line. Achondroplastic dwarfism. What is achondroplastic dwarfism? You'd have long bones stopping to grow in a childhood, resulting in normal torso, but short limbs. So the rest of the body grows fine. It's just the appendicular skeleton. So the long bones, the femur is never going to grow no more. The tibia and the fibula, not going to grow no more. And the rest of the bones of the humerus and the ulna and the radius, they're not going to grow at all. So it's caused by, so what's the pathogenesis? There's a failure of cartilage growth in the metaphysis, and there's a spontaneous mutation that produces mutant dominant alleles. So in contrast to pituitary dwarfism, there is a lack of growth hormone, and there are normal proportions with a short stature. So this is not pituitary dwarfism. In pituitary dwarfism, everything is small. But this one is only restricted exclusively to the long bones only. Bone widening and thickening. You would just see that the rest are like the feet, like the legs, and I think there was one like that on the news. He was a gang member, and they brought him in the court, and the body was defined, but the appendicular limbs, they were really dwarfed, and he shot somebody. So he was all over the news. This was a couple of weeks ago. You didn't see the news?
No.
Yeah. Yeah. There was.
I know, it's like too much noise.
Yeah. You gotta watch the news. You gotta know what's happening around you. That's very important.
Everything that is important is not assignment to any incident.
Yeah, but you gotta see what's happening. You cannot be living under a rock. You gotta know. Okay. Bone remodeling. So bones continually remodel. They absorb and deposit, replacing 10% of the skeleton per year. So your skeleton is not the same over a lifetime. So 10% is replaced per year. So every 10 years, your entire skeleton had to make open. Because 10% is replaced every year.
Yeah, that's why you get short.
This is why you get short? So it repairs the microfractures. That's what's gonna repair the microfracture. It releases minerals into the blood, reshapes the bones in response to use and disuse. What's Wolff? Law of the bone. Says that the architecture of the bone is determined by mechanical stresses placed on it. If you're a construction worker, you're gonna be really strong because you're stimulating your bone to adapt to the stress. Same thing with somebody working out every day. So their muscles and their bones are going to get really strong to keep up with this daily stress they go to. So remodeling is a collaborative and precise action of osteoblast and osteoclast. You would have bony processes that grow larger in response to the mechanical stress. Now, mineral deposition and resorption. So mineral deposition, known as mineralization or crystallization process, in which calcium phosphate salts and other ions are taken from the blood and deposited in the bone. So what is that in response to? If you're going to take calcium from the blood, deposit it in the bone, what is that in response to?
You're talking about osteoclast?
So that when you see what it says there, crystallization process in which calcium phosphate and other ions are taken from the blood and deposited in the bone. So what does that tell you? That's a response to? Exactly. That means that's a response to regulating hypercalcemia. So osteoblasts produce collagen fibers that spiral the length of the osteome, and fibers become encrusted with minerals, and the first few crystals act as seed crystals that attract more calcium and phosphate from the solution. Then there's ectopic ossification. Ectopic ossification. In ectopic ossification, there is abnormal calcification of the tissues, such as lung, brain, eye, muscle, tendon, or the artery. That is arteriosclerosis. In ectopic ossification, you would have this abnormal calcification of the tissues, such as you have abnormal calcification of lung, brain, eye. You know, sometimes the valves in your heart, they get calcified. So when the valves in the heart get calcified, that's stenosis. They get narrower. So now what problem is that? That means your heart has to pump harder now to exactly. So now the muscle of the heart is going to get thicker to keep up with this blood that we're going to try to pump out. Calculus, that is a calcified mass in an otherwise soft organ, like the calcification of the heart. Now, resorption is the opposite, is the degradation, removal of the process of dissolving bone, releases minerals into the blood. It's performed by osteoclast, C-class cut, at a ruffled border. Hydrogen pumps in the membrane secrete acid, hydrogen into the space between the osteoclast and the bone surface. The chloride ions followed by electrical attraction. Then you have, if you have hydrogen and chloride, what is that going to come out to? Hydrochloric acid. And that's going to dissolve and degrade my bone tissue. The acid-tolerant protease enzyme digests collagen. So the orthodontic appliances like braces reposition the teeth through resorption and deposit. So the tooth moves because osteoclasts dissolve the bone ahead of the tooth, and osteoblasts deposit the bone behind the tooth. We talked about calcium homeostasis, where calcium need for bone structure, neuron communication, muscle contraction, blood clotting, and exocytosis. They did not mention the one thing I said earlier. What did I say is too bad when there's too much calcium? What did I mention that was too dangerous if you have too much calcium? If you have hypercalcemia, you gotta turn on something on that was supposed to be off. An enzyme like an autocatalytic, destructive, destroying, degradative metalloproteinase enzyme. So the minerals deposited in the skeleton and withdrawn when they are needed for these other purposes. About 18% of the skeletal calcium is exchanged with blood each year. So a normal calcium concentration in blood plasma is 9.2 to 10.4 milligram per deciliter. In hypocalcemia, calcium deficiency causes excessive excitability of nervous system and muscles. Hypercalcemia is when there is calcium excess and it causes the nerve and muscle cells to be less excitable than normal. So it's dangerous when you have too much calcium because it's going to cause an increase in arrhythmia. It's going to cause arrhythmia and increase in excessive excitability. So it's very interesting how, yeah. So if there is hypocalcemia, that is going to, because you know calcium is supposed to cause the plateau phase. The plateau phase in the membrane action potential of the cardiac myocyte. So now when you don't have enough calcium, that means you're not going to have plateau. So then you're going to be over excited.
Okay.
But when there is hypercalcemia, you're going to have too much plateau. And that is going to, is that clear?
Yes.
I don't think it is. So we know that the action potential normally everywhere looks like that. P wave, Q. Oh, you guys don't know the action potential yet?
No.
Okay, then that's gonna be.
That's
That's gonna be in the. No worry, we're gonna come to that. I forgot. I'm teaching many classes. Yeah, you're gonna see that usually all the tissue look like this: the P wave, Q, R, S.
Oh, you're talking about the EKG.
T, yeah, the EKG. It's supposed to look like that. Then P, Q, R, S, T. P, Q, R, S, T. For the heart, it's gonna go P, Q, R, then it's gonna go along, then you're gonna have S and a T. Then you're gonna have P, Q, R, then long, then S and a T. Then it's gonna look like that. You see this here, that's the plateau. That plateau allows for the filling of blood in the heart. You need that delay. So you didn't drop down as sharply as you should.
So you won't have a love dub. The heart won't go love dub. You won't be.
It's gonna go love dub faster than it should. It's not gonna go love dub. It's gonna go love dub 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 like that really quickly. Why? Because you're gonna drop from R to S quickly, but here you're gonna go from R to S in a longer time. You're gonna slow down so that you can fill blood. You don't want to prematurely contract. You don't have enough blood. So in high, and the calcium is the reason. The calcium influx is what's gonna offset the potassium efflux. You don't even know what I'm talking about. That's why I said to them when we get to the neuron, we're gonna see. It's the potassium repolarization is what's gonna cause this drop. This drop from R to an S, that's the potassium repolarization. So while this is everywhere in the body, it goes like that. But in the heart, calcium is saying, I'm gonna slow you down. I'm not gonna let you go down as fast as you should. I'm gonna open up and calcium is gonna influx.
Because of the hypercalcemia and less excitability.
So because there is too much calcium now, you're gonna have too much plateau. When you have too much plateau, that's gonna make the excitability really impossible now, refractory. But when there is hypocalcemia now, you're gonna become like an epithelial cell. Your heart is gonna be like an epithelial cell. So it's gonna contract prematurely. Not even enough blood, not even full with blood is contracting.
So be hypotension.
Will that cause hypotension? No, that's gonna cause hypertension because it's
No,
pumping.
it's going slow. You said because it's gonna relax.
Yeah, so if it's going too slow, that's hypotension.
Hypotension, that's
Yeah.
what I'm saying.
Very good. Very good. You guys are being good physiologists today. I don't know why. Excellent. You guys have been excellent anatomists and physiologists today. Okay. Calcium homeostasis. Now we knew what happened with hyper and hypo. Now we need to see who are the hormones that make that possible. So knowing that we restore hypercalcemia into hypocalcemia into eucalcemia is not enough. We need to know who are the actual hormones that are responsible for that. Number one, calcium homeostasis depends on a balance between dietary intake, urinary and fecal losses. So you know, if you eat too much calcium, that's a problem. If you lose in the kidney too much calcium is a problem. So the calcium homeostasis is regulated by calcitriol, calcitonin, and parathyroid hormone. So now let's look at these hormones, what they do. So obviously we take calcium with calcitriol. Calcitriol is like a vitamin D. It's going to help absorb calcium from the intestine. And calcitriol also helps absorb calcium. So calcitriol always brings calcium into the blood, whether bringing it from the intestine or whether bringing it from the bone. Doesn't matter where you're bringing it from, you're still going to bring it through calcitriol. Parathyroid hormone is the one that is going to degrade the bone. While calcitonin is going to take bone from the blood, build up the bone. That's very important. Calcitonin will take calcium from blood, dump it in the bone when there's too much calcium. And PTH, when there is too little calcium in the blood, will take it from the bone with the help of calcitriol, who's going to bring in blood from the intestine. So calcitriol is a form of vitamin D that is produced by sequential actions of the skin, the liver, and the kidneys. So the epidermal keratinocytes use ultraviolet radiation to convert 7-dehydrocholesterol to pre-vitamin D. And warm sun on the skin converts this to vitamin D, cholecalciferol. So you see that your integument, your skin, is responsible. These epidermal keratinocytes use ultraviolet radiation to convert 7-dehydrocholesterol to pre-vitamin D. And the warm sun on the skin converts this to vitamin D3, cholecalciferol. The liver adds hydroxyl group, converting that to calcidiol. And the kidney adds hydroxyl group, converting that to calcitriol. And calcitriol acts to raise blood calcium in 3 ways. It increases calcium absorption by the small intestine. It increases calcium resorption from the skeleton. And it weakly promotes reabsorption of calcium from the kidneys. Calcitriol is also necessary for bone deposition, helping provide adequate calcium and phosphate. Inadequate calcitriol results in abnormal softness of the bones in children, known as rickets. So what's the difference between rickets and osteomalacia? They are the same in the sense that they have soft bone tissue. The only difference is rickets happen in children, R with the R. Ricket, children, rickets, children. While osteomalacia, L, adult. Osteomalacia, L, adults. Yeah.
become bow-legged as an adult? Like if you have straight legs all your life, you become bow-legged?
It continues. So you move from rickets. It
As you get older.
Yeah, as you get older, sometimes if you have a severe deficiency, so that they're not connected. They could connect. They could start at rickets, and you get older, you have osteomalacia. But you could be old enough, and due to some problem with calcium homeostasis, you have a soft bones. So now that's osteomalacia. And both are treatable, by the way. Both are treatable. It's not the end of the world. You can treat rickets. You can treat osteomalacia. Yeah. You give them vitamin D helps a lot, and to improve calcium homeostasis is going to improve a lot of the quality. It's not just the sun. So you have to know what is the actual problem. Is it a problem with the homeostasis of the calcium? Is it a hormonal problem? Is it a glandular problem? But it's not a terminal disease. That was calcitriol, vitamin D. Now there's calcitonin. That's produced by the parafollicular or the C cells of the thyroid gland. They're secreted when the blood calcium levels are too high. They lower the blood calcium concentration by two ways. They inhibit osteoclast, because imagine you already have too much calcium and the osteoclasts are working, degrading the bone tissue and thereby reducing the bone resorption. Or by osteoblast stimulation, they stimulate a deposition effect of the calcium into the bone. It's important in children and it has weak effect in the adults. Osteoclasts are more active in children due to faster remodeling, and they may inhibit bone loss in pregnant and lactating women. The negative feedback loops in calcium homeostasis, that shows the correction for hypercalcemia. So you need to know this loop, that when too much calcium, we secrete calcitonin, too much calcium, calcitonin, too much calcium, and that's going to work by reducing osteoclast activity and improving osteoblast activity. But when that's going to lead to less bone resorption, and that's going to drop the too much calcium level in the blood. We're going to end the too much calcium level in the blood. Now, parathyroid hormone, PTH, is secreted by parathyroid gland on the posterior surface of the thyroid in response to low blood in the calcium. Yes. The parathyroid hormone raises calcium by 4 mechanisms. The first one is it binds to receptors on the osteoblast, which then stimulate osteoclasts to resorb the bone. They promote calcium reabsorption by the kidneys, and they prevent the calcium loss in the urine, because we want to conserve calcium in the urine. They promote the final step of calcitriol synthesis in the kidneys, enhancing the calcium raising effect of calcitriol. They inhibit the collagen synthesis by osteoblast, inhibiting bone deposition. So they inhibit the collagen synthesis by osteoblast because we want to break down the calcium. Yeah.
So it's taking it from the bone into the blood?
Yes. From the bone into the blood, because we have a deficiency. We have too little. So we need to stop collagen because we don't want to build bone. We want to destroy bone. And then we promote the resorption. So we activate the osteoclast. There you go. A drop in blood calcium leads to a drop in blood calcium deficiency, and there is a parathyroid hormone secretion, and that leads to increased osteoclast activity, reduced osteoblast activity, and there is more urinary excretion, and there is less urinary calcium excretion. That is the correction for hypocalcemia. We secrete PTH, is going to prevent the loss of calcium in the urine, prevent the loss of excretion of calcium, and it's gonna stop building the bone, and it's gonna start degrading the bone, leading to more bone resorption, less bone deposition, and prevention of hydroxyapatite formation and conservation of calcium. Now, if we look at phosphate, so now phosphate is the other difference between calcium. So remember, we don't only have in the bone calcium salt, we have calcium and phosphate. So the average adult has about 500 to 800 phosphorus, with 85 to 90% of it in the bone. The normal plasma concentration of phosphate is 3.5 to 4. So phosphate is also needed in the DNA, RNA, ATP, and the phospholipids. Phosphate levels are not regulated as tightly as calcium levels. So calcitriol raises phosphate levels by promoting its absorption by the small intestine. So the parathyroid hormone lowers the blood phosphate levels by promoting its urinary excretion. Other factors affecting the bone are there are at least 20 more hormones, vitamins, and growth factors that affect the osseous tissue. So the bone growth, especially rapid in puberty and adolescence, there are surges of growth hormone, estrogen, and testosterone that occur and promote the ossification. These hormones stimulate multiplication of osteogenic cells, matrix deposition by osteoblast, and chondrocyte multiplication and hypertrophy in the metaphysis. Girls grow faster than boys and reach full height earlier, and estrogen has stronger effect than testosterone on bone growth. And anabolic steroids cause the growth to stop as epiphyseal plate closes prematurely and results in the abnormal short adult stature. We end with the bone diseases. First of all, we have the orthopedics. Orthopedics is the branch of medicine dealing with the prevention and correction of injuries and disorders of the bone, joints, and muscles. The name here implies its origin as a field treating skeletal deformities in the children. I really think this slide here is very important when it comes to phosphate homeostasis. That we studied in the past that phosphate is a part of the nucleotide. We have the phosphodiester bond in the DNA. So phosphate levels, they're not regulated as tightly as calcium levels. So calcitriol raises phosphate levels by promoting its absorbance, while PTH lowers blood phosphate by promoting its urinary excretion. So you see calcitriol has the same effect on phosphate as it does on calcium. It increases it in the blood. Okay. Bone fractures are classified as stress fracture or pathological fracture. Pathological fracture is a fracture that is caused by a pre-existing pathology. Like you have a disease, maybe like kidney failure, you are unable to reabsorb calcium, so you're losing too much calcium, your bone get weaker, your bone breaks. That's a pathological fracture. It is caused secondary to some original disease that caused the bone weakness. But stress fracture is caused by abnormal trauma to the bone, like when you fall, some mechanical damage. But pathological fracture is a break in the bone that is already weakened by deteriorating bone, such as bone cancer, osteoporosis, usually caused by a stress that would not break a healthy bone. Fractures also are classified by structural characteristics. So the direction of the fracture line is such as non-displaced or displaced. It is cracked or in multiple pieces, such as comminuted or green stick. So a fracture is in a break that is a break in the continuity of the bone as a one long piece. So you do not have a bone as a long or the one long piece. It breaks. So that is a fracture. Sometimes the bone can break completely, complete fracture. Sometimes you can have a partial fracture. So that's a non-displaced. That's a displaced fracture. That's a comminuted. What's a comminuted fracture? A comminuted fracture is a fracture where the bone breaks and there is like brittle and there is like fragments and powder, bone powder. But green stick is for children, pediatrics. Now the healing of fractures, yeah, is abuse and sometimes when they just fall. Like it doesn't have to be exclusive to abuse. So there are other causes. It's just due to a abnormal trauma to children. So, but definitely, one of the major causes is the abuse. Definitely, uncomplicated fracture heals in about 8 to 12 weeks. It's longer for more complex fractures. So, did you guys do the healing of a bone fracture? You see, the first step is the hematoma formation. There is a blood clot. There's a fracture hematoma converted to granulation tissue. Then there's a soft callus formation, where it's deposition of the collagen and the fibrocartilage converts the granulation tissue to soft callus. Then there is hard callus formation, where osteoblasts deposit temporary bony collar to unite the broken pieces while the ossification occurs. And bone remodeling is when small bone fragments are remodeled by osteoclast and osteoblast deposit spongy bone and convert it to compact bone. So you see that's the hematoma formation. The hematoma is converted by granulation tissue, by invasion of cells and blood capillaries. The soft callus formation, you have the deposition of the collagen and fibrocartilage converts granulation tissue to a soft callus. In hard callus formation, osteoblasts deposit a temporary bone collar around the fracture to unite the broken pieces while the ossification occurs. And lastly, you would have small bone fragments that are removed by the osteoclast in the remodeling, while osteoblasts deposit the spongy bone and convert it to compact bone. You see that's the hematoma. The hematoma is like a blood tumor, blood cushion, is converted to granulation tissue by invasion of the cells. So you know the immune system is active. The immune system is going to be recruited to the site of the trauma, and there's going to be a lot of inflammation, and there's going to be a lot of necrotic debris. There's going to be a lot of bacteria. There's going to be a lot of pain and redness, heat, swelling. Then the next phase is after the classical pathway is done, we shift to the alternative pathway. The alternative pathway is the soft callus formation. There is a deposition of collagen and fibrocartilage that converts granulation tissue to a soft callus. Then hard callus is going to form where osteoblasts deposit a temporary bony collar around the fracture to unite the bone pieces while the ossification is occurring. And lastly, you have small bone fragments are removed by osteoclasts while osteoblasts deposit the spongy bone and then convert it to a compact bone. How do we treat fractures? There's open reduction, internal fixation, known as ORIF, and there is closed reduction. Closed reduction is a procedure in which the bone fragments are manipulated into their normal position without surgery. So here we manipulate the bone fragment without surgery. While open reduction internal fixation involves surgical exposure of the bone and the use of plates, screws, or pins to realign the fragments. Fractures taking more than 2 months to heal may be treated with electrical stimulation, which suppresses the effects of the parathyroid hormone. Open reduction, internal fixation of a compound fracture. Other bone disorders are, beginning around age 40. There's a net loss of bone mass as the resorption now is going to outpace the bone deposition. So contributing factors are the sex. So women are more affected than men due to the menopausal osteoporosis. The build also small light frames affected more than the heavier people. Also, the ancestry white women of Asian and European origin are very vulnerable, and older individuals are more vulnerable than the younger. Osteopenia is a measurable decline in bone density, and it may advance to osteoporosis. So when they do the DEXA scan, and they get the record, that shows you that osteopenia comes before osteoporosis. And lastly, there is a severe loss of bone density and bones easily fracture. Common assessment procedure. The bone densitometry or the DEXA scan scans the spine and hips with low dose x-rays. The treatment strategies center around the drugs that stimulate the bone deposition or slow the rate of the resorption. There are preventative methods that include the weight-bearing exercise throughout the life, even the old age. You see spinal osteoporosis? That's spinal osteoporosis. You see, the osteoporosis means the holes get bigger and the bone get weaker. Okay, so